Alright, now we're looking at problem number 5. So some more partial fractions. So what differentiates these from the other ones is the fact that when we work them, whether they're factored or not, is that they're going to have these simple quadratic factors, or in other words, quadratic factors that don't factor into smaller ones. So no real roots. You can think of it that way. But let's start number 5a. Look at the integral dz over z squared plus z to the fourth. So what do? This is integral dz. Then we factor. Sometimes you'll have to factor on these problems. This one is fairly easy, c squared plus 1. And now we say, okay, I have a z squared and a z squared plus 1. So you take this thing, and then copying it down, I can change this dz to a 1 and say this is equal to a over z plus b over z squared plus, and now here's where I need the fact that z squared plus 1 is simple quadratic. I can't factor it, so I can't turn it into linear terms. So what the partial fraction strategy says is this is z squared plus 1 over cx plus d. And now we have to solve this for a, b, c, and d. So what do? I multiply both sides by the denominator. So this is going to become 1 equals, but let me save myself some room, and maybe you'll see why in a second. So I get a times the z squared, I'll leave a z, and then just z squared plus 1, plus b. Both z squareds go away, so I'm just left with z squared plus 1. And then I'm left with cx plus d. This x should be a c, or a z. cz plus d. And then the z squared plus 1 cancels, so I'm left with z squared. And what's the trick here? If I look at this, I'm going to get z cubed, z squared, z cubed. So I can write this as plus 0z plus 0c squared, 0z cubed. And why do I do that? That's so that I can do what I did in the previous problem where I combine all the like terms, the one that have the same power of z. But let's go ahead and factor this. So this is az cubed plus az plus bz squared plus b plus cz cubed plus dz squared. And that's it. So how many terms? 1, 2, 3, 4, 5, 6. And that's how many that I have. And so I can copy this down. 0z plus 1. And now I do that same trick that I did in the last problem where I look at everything that has a z squared in front, or a z cubed. So this equation says 0 is a plus z. Break out green. Now I look at everything in front of a z squared. So there's a b and there's a d. So 0 equals b plus d. Let's do blue. Everything that has in front of a z, so a, and that's it. So 0 is equal to a. And then finally, purple, 1 is equal to b. Okay, so this is pretty great because this makes doing this fairly easy. So a we know is equal to 0, b is equal to 1, b plus d equals 0. That implies 1 plus d is 0, so d equals minus 1. And then finally, c is a plus c, or sorry, 0 is a plus c, a is 0, so c equals 0. And we get integral 1 over z squared, or dz, z squared plus 1 is equal to the integral of b, which is 1 over z squared, and then plus integral minus 1 over not x but z squared plus 1 dz. Okay, so now we need to do these two integrals, but these are actually both very reasonable integrals. So this is integral z to the minus 2 dz minus integral 1 over z squared plus 1 dz. So finally we get minus z to the minus 1 minus, this is one that students sometimes get tripped up on. So you might do a trig substitution or try a u substitution and that doesn't work, and you scratch your head and you say, man, this integral looks hard. But it's good to keep in mind this is just the tan inverse of z. Right? Derivative of tan inverse is 1 over z squared plus 1. So that's a thing that students sometimes forget, but it really does show up on these sometimes. And so finally, I get my final answer is 1 over z minus tan inverse of z plus c. One day I'll circle it all. Okay. And I want to be really careful because here it turned out a was equal to 0 and c was equal to 0, but by no means does that have to happen. A could absolutely be some number other than 0, c could be some other number than 0. So just be careful that you don't forget the a over z term or the c term in the blank over z squared plus 1, because you could get into a lot of trouble that way. Okay, so that is part A. Now let's look at part B. So B, this one's probably going to take 2 pages, but that's okay. Integral x squared plus x plus 1 over x squared plus 1 squared. Okay, so this is the what do we do when we have a repeated linear term case or quadratic term case. So again, x squared plus 1 can't be simplified anymore, so that's the best we can do. So this, once again, I'm going to use the power of technology to save myself some time. That this is equal to, and now what we have to do is we need an ax plus b for the first x squared plus 1, and then we count up cx plus d over x squared plus 1 squared. And now we solve this. So multiply everything by this denominator, and I'm left with x squared plus x plus 1 is equal to ax plus b times x squared plus 1, because I have 2 of them here, but only 1 of them here. So then you get plus cx plus d. So now this is 0x cubed plus x squared plus x plus 1 is equal to ax cubed plus bx squared plus ax plus b plus cx plus d. So let's look. I have a 0 in front of the x cubed. I have a 0 or I have an a in front of the x cubed, and that's all those terms. So by the pink, a is equal to 0. By the purple now, I have 1 in front of x squared. So 1. I have a b in front of this x squared, and that's it. So b is equal to 1. And now here's where there's some amount of work. There's 1x, there's ax, and there's cx. So c is equal to, or c plus a is equal to 1. That gives us c immediately, but let's wait a second. And then finally, the last term, we haven't done green yet, is this 1. So that gives you b and d. And so b plus d also is equal to 1. So a equals, b equals, c equals, d equals, a is equal to 0, b is equal to 1, nothing fancy there. C plus 0 equals 1, so c is 1. B plus 0 equals 1, or, sorry, b was 1. So 1 plus d equals 1 means d is equal to 0. So we're left with this integral that I am once again going to copy and, oops, paste. This is equal to, what was b? B was the constant term. So 1 over x squared plus 1 integral dx plus the integral of c, which is 1, so x over x squared plus 1 squared dx. And now we have to harken a little bit back to Cal 1 for that right integral. This left one isn't bad. This, once again, is tan inverse of x. Nothing crazy there. But for this, we're going to need to look at, let me do some scratch work. Integral x over x squared plus 1. What do you do here? Let u be squared. Did I write squared here? Yes. Let u be x squared plus 1. Then du is 2x dx. Okay. So this integral becomes 1/2 integral du over u squared, which if you integrate that using power rule, you'll get minus 1 over 2u. The u squared becomes a minus 1 over u to the minus 1, which is minus 1 over u, but then you've got that 1/2 out front. So this is minus 1, 2 x squared plus 1. So let's go ahead and throw that in there. This is minus 1 over 2 x squared plus 1. And then you add in plus c. Okay. So that's number 5. Not the most fun thing in the world, but not really as bad as you might suspect. Again, you never know if something's going to be 0 or not. It could absolutely not be. So that's something to watch out for. Also, if I did end up getting an integral, say I had integral of ax plus b over x squared plus 1, where a and b weren't both 0, then this would mean, how would you fix that? You would just break it up into 2 integrals. X squared plus 1. So you would break it up into 2 integrals and then do each one separately. This one you would use a u sub. This one you would do, it would be a tan inverse.